Well, regarding the neighborhood structures or the operators in order to produce the neighbors, they are usually very coupled with the encoding. If we are using a binary encoding, then typical operators are one flip, which chooses one variable of the solution and flip the bit, or perhaps two flips, three flips, and so on. Or you could also consider smarter changes, such as changing 1 0 and 1 1. So you are kind of swapping these values. If you are using integer encoding, then the classic operators are one change, two changes, and so on. And the idea of one change is to select one variable of the solution and draw a new value for that variable. If you are using the uh, permutation-based encoding, then you could consider to swap operator, perhaps more swaps, also to OPT, to swap just swaps the values in two random positions. To OPT swaps the values in two random positions, but also inverts the values in the middle. In real value encoding, then typical operators is to add some noise, add some normal noise. Mean zero and standard deviation, whichever you consider is best for your problem. And finally, for trees, subtree mutation, which is the idea of removing a subtree of the tree and producing a new random subtree from the taken node. Well, perhaps you have noticed that these operators sometimes produce large neighborhoods or small neighborhoods. For instance, one flip produces neighborhoods with n neighbors, as many as variables in the solutions, and two flips produces, well, not this much, but around n to the square neighbors, and so on. In the case of swap, it is similar. This is similar to n to the square, the same here, n to the square. And if we consider more swappings, then this function increases. So what are the advantages and disadvantages of large or small neighborhood structures? Well, if you are using large neighborhoods, then you are able to make large steps. If you are using small neighborhoods, then your steps are smaller. But an advantage of small neighborhood structure is that in order to evaluate the complete neighborhood, you take less computational time than the necessary for evaluating this large neighborhood. Obviously, as we have said, we can compute the size of the neighborhood, and this is something that we will consider later, but an interesting point is that in order to evaluate the neighbor of a solution, perhaps computing the quality of the solution is more complex than computing the quality of this change, the quality change. So if you got the fitness of the previous solution, then you could add this change in the fitness and this way you obtain the fitness of this neighbor.